Okay, so I think now you are seeing my screen and we are all good to go and I'm taping. So chapter 3 emphasizes laws of motion and chapter 3 has a lot of physics in it. And in general, I cut all of it except the physics that explain gravity force, the force of gravity. Why? Because it's one of the fundamental forces of nature, and more so is the one responsible for forming not only stars but also planets, planetary systems, is the one responsible for keeping the moon going around Earth, Earth around the sun, for keeping the galaxies held together by hundreds of billions of stars, all glued by this force we call gravity. Um, so the law of the gravity, as we are going to explore in chapter 3, came to fruition after a major development in the way we see science. Up to Galileo Galilei in the 1600s, you would exercise science in a very primitive way. I mean, we had technology since ancient Mesopotamia and India, China. There was technology in place, and we observed the natural cycles of nature, and we would come up with empirical laws to explain those motions. But to explain exactly, or in fact, the empirical laws were there more to reproduce and to predict events. But the explanation of events really didn't exist, was not a major requirement. Um, in Galileo Galilei in the 1600, he came with a different way of tackle the reality we have in nature, in that sense that you observe things, you observe the sun rising in the eastern sky and set in the western sky. You observe this happening again in the following day, and then again and again and again, and then you ask the question, why this happened? And when you try to explain why this happened, after Galileo Galilei, you have to establish some hypothesis. And that hypothesis cannot be any hypothesis like, well, the sun rises because is God Apollo in his chariot going across the sky, delivering heat to all of us because Apollo is the god sun. So this is not a valid hypothesis because you cannot bring God Apollo to your laboratory and make a detailed study of gravity based on the God that you cannot summon and you cannot explain exactly what it is. One of the major problems I found with the discussion in astrology is that for most of the students who believe in astrology, astrology is a religion. And as a religion, it's very difficult to come up with facts that support a religious belief, exactly because you don't need them. Any religion, so if I'm Christian or Buddhist or Hindu, it doesn't matter, or Muslim. So if I have a religion, I do not look for proofs in support of the argument or statements that my religion profess. I just believe. And no matter what arguments will come, I will not accept them because I have a belief that goes into my being and that cannot be changed. Science is different from that. When you make a statement in scientific arena, like we do in our book, like we do in classroom, so when we do these statements, you should be able to back up your statement with proofs, with some evidence. And that evidence should be able to be reproduced by other researchers in different laboratories under different conditions, as long as they have the means to summon and to bring the technology that allows those data to be taken. So science is different from religion, and then for some students to explain why for them astrology is a true thing, it is a scientific and it's based on true facts, it's very difficult for them to come up with explanation, because it's more like a belief. My parents taught me that, and I use the horoscope that I read every day to pave my life, basically. And so I read it, and then I have some intuition, and then I follow that through. So this is a religious way of facing astrology, which is not scientific. Just a second. Hello? Oh. Okay, so Galileo Galilei, there was observations done, and let me bring the Starry Night software. And your planetarium software has some similar features. And I will show some of the observations that led astronomers, not astronomers, but basically philosophers, to come up with different worldview as to why planets behave the way they do. So if I look to this display, it's 7/17, September 18, 2017. It's pretty much as it is now. We have Saturn in the sky, Jupiter is setting over there. Those of you who could go to the star viewing on Friday, you had the chance of observing these planets. But what I'm going to do here is to get rid of daylight. There you go. And to bring the line called ecliptic. And the ecliptic line is a line the sun is always located, and is also the name of the plane that is the orbital plane of Earth around the sun. And I will bring the labels of planets and moons. So Saturn is in there, Jupiter is setting over there, Pluto is a dwarf planet. Now, if we allow time to speed up, that is what happened. We see the sky objects in case we are facing the southern direction. And if you are taking the astronomy lab class, or if you have gone to the observatory, or if you had gone to the stargazing, you know you face straight south, and then you see the sky moving and migrating from eastern to the western sky, exactly as you see in the simulation. So this is caused by Earth rotating on its axis. And then you can realize that time is speeding up, the time is moving fast, as you can see up here. Okay? And then Pluto is going to be setting. All right. Now, as we did last week, imagine that I have the ability of facing the same sky object, the same constellations. And which constellations I have here? I think Capricorn, Scorpio is gone. Let me bring to the time now. So there you go. So Scorpio is right here. The constellation Scorpio is right there. Let's see if I can bring the Scorpio on view so you know what I'm talking about. There you go. So that is Scorpion right here. You can't see well with all this illustration, but it gives you some idea. And Sagittarius coming after, Capricornus, and then Aquarius, so it's right there. And this green line is the ecliptic line, which indicate the path of the sun throughout the years. And those are the constellations of zodiac, those where the green line happen to be projected. So again, I'm going to take these illustrations out. And then I'm back with the planet, and what I would do is to change one day at a time instead of speeding up the time from, let's say, 1 second every second to several minutes every second, as we were doing before. So in other words, I'm going to see not necessarily how Earth rotates on its axis and how the sky appears as Earth rotates on its axis, but what I would do is I'm going to be facing the same sky object all the time and then see which planets happen to be moving across my field of view. So if I do that, look at this. The moon, in respect to the stars that I keep facing all the time, every day the moon moves a little bit to the left. The moon moves a little bit to the eastern part of the sky. So look at Jupiter. Jupiter is slowly, right here, Jupiter slowly comes out from the western sky and slowly move towards east. But look what happened now. Jupiter is going backwards. Jupiter is what we call retrograding. Like Mars is retrograding right now. And then Mars is going to start prograding again like Jupiter. Sun is always prograding. Venus is prograding now, but pretty soon might start retrograding. No, it didn't appear. Saturn is prograding. Ceres is retrograding. Look at that. And now we start prograding. So progression is the apparent motion of planets in respect to the background stars from west to east. And retrograde is when this apparent motion is such that the planet goes from eastern part of the sky to the western part of the sky. Okay, so the philosophers knew about that, and here is an illustration of what they could mark. The constellation on view here is Cancer. So those lines that look like a triangle is Cancer. So you have a planet that comes, slowly every week or so. You observe that planet. That planet seems to be going eastward, seems to be going prograde. But then the planet stops and then retrogrades. Look at that. Retrogrades and then progrades again. So to explain this apparent retrograde motion of planets in the sky, the astronomers, in fact, Ptolemy, Aristotle, and Exodus, all these ancient philosophers, they come up with a worldview in which Earth was in the center of the universe and these planets were orbiting Earth, describing epicycles. So if Earth is over here, the planet would go in an epicycle, retrograde, prograde again, and then retrograde, prograde again. Is an orbit that requires circles and more circles. Okay, so the precision to explain and to predict planet positions using circles and epicycles as done by Ptolemy and pretty much following the philosophical guide of Aristotle, it was done up to when Kepler, Johann Kepler, he discovered the laws of planetary motion. So the 3 laws of Kepler. And the first law of Kepler, it states that planets go around the sun in a type of curve that is called ellipses. And so ellipses have 2 foci, and in one of these focus the sun is located. So that is the first law of Kepler. For instance, the moon goes around Earth, not in a circular orbit, but go around Earth in an elliptical orbit. And Earth has happened to be located right at the focus of this ellipse or this path. That's the first law, and this law is good enough to explain the motions of planets around the sun, satellites around their planets, stars around the center of the galaxy. Kepler's law works quite well. The second law of Kepler is a consequence of the fact, oh, by the way, the ellipses can be elongated or not. An elongated ellipse is the one that is flattened, like this one. It has a high eccentricity, whereas some ellipses the eccentricity is so-called zero, and that is the shape of a circle. So the planets that go around the sun, they go in elliptical orbit, but the eccentricity of these orbits are almost zero. And then when we trace them, they appear to be nice circles, but they are not. They are elliptical paths. So a class question, does Kepler's first law allow for a circular planetary orbit? Oh yes, it's a special case of ellipses. So ellipses can be flattened, but can also, in a special case, is a circle when the eccentricity of that ellipse is pretty much zero. And that's how it is in there. So the second law of Kepler, it has some mathematics on it, and that was fully explained in the 1700s by Isaac Newton. And for him to explain that, he had to develop calculus, because his main task was to calculate the area of these blue or green or pink curves. So what is the second law of Kepler? Well, the second law of Kepler is this. If you take a line and connect a line from the planet to the star and allow that line to be sweeping out an area as the planet goes around the sun, and if you're able to calculate how many square inches or square kilometers or square miles or square light years that area is, the planet should pass from point C to point D. The line connecting the planet to the sun should sweep out equal areas as it progresses in its path the same amount of time. Now, if you look at the planet when it's closer to the sun, the area in green here should be equal to the area in pink here, as long as this time is the same. So this time, the time that takes the planet to go from this dot to this dot, is the same as it is when it goes from this dot to this dot, as long as the area is the same. And Kepler was able to determine that just based on observations. He was a mathematician, but he inherited valuable data from Tycho Brahe, and then he was able to find this relation. But what is the beauty of it? Well, if you look at the path from this point to this point, the path is much longer than it is here, right? So let's say you have 1/3 of an inch here, and you have a path that is almost 1 1/3 of an inch here, right? It's bigger. So if the time that takes the planet to go from this point to that point is the same as it takes to go from here to there, it implies the planet goes much faster in here than it goes in there. Like, if you have to go from Evergreen to your home, you take some time. But if you have to go from Evergreen to, let's say, Morgan Hill, in the same time, you have to go faster, or you can't make it on the same time. Okay, so Kepler's second law sometimes is enunciated in the following way. is the laws of equal areas, equal amount of time. The planets describe and sweep out equal areas in equal amount of time, and what implies is when the planet passes closer to the sun, it goes faster and it speeds up. The average speed is much larger than it is when it's further out. And the third law of Kepler is a law that relates the average distance of the planet, which is the semi-major axis, with the time the planet takes to complete one revolution, which is the so-called sidereal period. So the third law of Kepler states that the period square is equal to the semi-major axis, which means the average distance of planet to the sun to the third power. It's just a mathematical law, and it happens to work. Now, Newton, about 100 years after Kepler, he developed the laws of gravity, and that's what I would like to show you, because it's the important point here. And I'm jumping all these laws of motion because we really are not doing physics. This is the law that you need to know. So Newton was able to explain with mathematics the laws of motion, and to explain that the force that keeps the moon going around Earth is the same force that allows a pencil or a pen to drop down to Earth from my hand. So the laws are basically the same, and gravity is the force that pulls the pen down. Gravity is the force that pulls the moon towards Earth. Gravity is the force that keeps galaxies together. And the intensity of that force, the magnitude of that force, depends on a constant, which is a number. This G is a number. 6.67 10 to minus 11 is a small number. Multiplied by the product of the two masses divided by the distance of these 2 point masses. So this is gravity. So gravity is a force that if the two masses are way apart, see this R here is a term that goes in the denominator. So if the masses are set apart, the gravity, the attraction between those two masses will be less than it is if you bring them closer together. So sometimes the stars are so far away, they ignore one another because the gravity, the bound of these stars are too weak, and they move through the galaxy without ignoring one another. But if stars get close enough, this R factor becomes smaller, and then gravity becomes an important factor, and the stars start interacting. Now, if the mass of the stars are significant, then the gravity force is going to be stronger too. Whereas if the gravity force is not that strong, the masses are not that big, the gravity forces will not be that stronger. So it is in the discussion of astrology, I had a few students who mentioned, well, no, astrology is true because, see, the moon exerts tides on us. Well, that's true, as well as Earth exerts tidal forces on the moon. So the forces are the same as we learn in physics. But the moon and the gravity pull between moon and Earth are important, and you can measure in the way the water bulges out a few feet a day, in fact twice a day. But this is the only one. So Jupiter, Saturn, they produce some disturbances on Earth as far as its orbital path is concerned. But the gravity pull of Jupiter to Earth is negligible, and probably the gravity force of this wall that surrounds me to my body might be more important than the gravity force of Jupiter on us. Also, light radiation exerts no significant factor. The radiation or the light that Jupiter reflects off its surface towards us, whereas the sun has an important contribution as far as light is concerned. So in physics, when we try to find influence, okay, what is the influence? So we are talking about force. So which sort of a mechanism can you come up to explain the actions of planets or constellations of stars over people's life? So if you can't come up with a mechanism that can be verifiable, then what you believe is more like a religious belief, which is okay, but it's not within the realm of scientific investigation. That's the point I try to emphasize in the discussion in the post that I wrote to some of you. So this is chapter 3. That is the importance of chapter 3, because this gravity force will appear again and again and again as the course unfolds. Okay? Any comments you guys would like to do? Did you all have dinner already? Okay, so that's all for chapter 3. Chapter 4, which we'll be focusing next week. Sorry, not this one. Is about light. Is perhaps the most important chapter as far as the whole book is concerned, because it's a chapter that explains basically how do we understand science as being, or astronomy as being scientific. I keep repeating that. Science is based on evidence. You have to bring evidence to your face, and you have to measure, right? So how can we talk about expanding universes and quasars and galaxies? They are so far away. We never collected any material from these objects. How can we talk about them if they are so far away? And the main point is, well, they are far away, but there is something that we collect of them, and we can analyze it, and we can talk about, because we know how to identify those things. Okay, wait a second. I'll come in a second. Sorry. All right, so what I will do now, I will stop taping, and then I can talk one-on-one to each one of you. Okay? So good evening, and I'm stopping taping here.